Hi, I'm Aina Nambina, and I use random forest analysis onto a couple of thousands of simulations from CAMEL to try to understand what is it that drives galaxies to quench their star formation. And I found out that in central galaxies, the supermassive black hole is the key indicator of whether a galaxy is forming stars or not. But in satellite galaxies, the random forest picks on different physics, on environmental effects such as halo heating or gas loss through interaction with other galaxies. And finally, we found that when varying the feedback parameters of the different simulations in CAMELS, the quenching trends are still kind of preserved. So we were wondering, can the quenching mechanisms learned from one simulation be used to predict quenching into other simulations? And we got some quite interesting results. Come check out my poster.
Whose poster was that? That's not my poster.
Thank you. And just also a reminder for the presenters, you also have the 1 minute clock there in case that's useful for you. I think we...
That's not me.
Is Akash here? No.
Is that you? No, that's not me.
Okay, sorry. Yeah, so this particular project is about trying to localize where you will find dark objects in the vicinity of bright ones. So for example, dark matter halos and very dim galaxies. We know that from gravitational clustering, we expect massive objects to be closely clustered with each other. But on small scales, we don't. Some of them might not be observable, especially like again very faint galaxies. But we can observe the very bright ones. So we want to see, using the closest distance to the bright neighbors, whether or not we can localize these dark objects and what's the probability of finding a dark object in the region of a bright one. If we take Kn statistics, so K nearest neighbors, where K equals to 2 for simplicity, and we plug in like this distance into a symbolic regression formula, we can find generally the probability takes this functional form. So the parameters can vary, but after running this Peiser symbolic regression package many times, we find the formula pretty much is pretty robust, like it stays with that form with different parameters. And that can visualize from the graphs above, where you can see like the dark regions are where you're not very probable to find the objects, and the brighter parts where the points are where we're more likely to find the objects. And here you can see that it actually does, if we take the correlation function, it does better. So, yeah.
Hello, my name is Alice. I'm at UCL and I'm working with Chris Lovell at the back, and I selfishly forgot to put his name on my poster, so I apologise. I'm giving a talk tomorrow, so this is a good little quick fire round, which I haven't prepared for. So I basically work with UV luminosity functions. My first project for my PhD was looking at observational data with XMM Newton optical monitor and the Swift UVOT, and so I've just started working with Chris on CAMELS data and using synthesizer to forward model photometry to generate our UV luminosity functions. And we are currently working on the Sobel sequence project using the 28 parameter set. And what we want to do is generate UV luminosity functions and train our neural network to predict the posteriors for these 28 parameters. And the end goal for this would be to get a good model that can constrain these parameters and then feed in my beautiful image that took 2 years to make into the model and get the predictions for the cosmological parameters. And the time is up. Sorry.
Okay, hi everyone, my name is Amanda Liu, and I am a third-year graduate student at Columbia University working with Shai. And my project is based on a project called Cosmology with One Galaxy, led by Paco here at the CCA. And that project basically found that using machine learning, you can infer the value of a megamatter using even one single randomly selected galaxy. And they hypothesized that this is because galaxies lie on a low-dimensional manifold within a higher dimensional galaxy property space that shifts with a megamatter. And what my project does is investigate how galaxies occupy this higher dimensional galaxy property space, and in particular, how a megamatter as well as other cosmological and astrophysical parameters affect this higher dimensional space. And we do this by using an autoencoder to do dimensionality reduction on galaxy properties from the CAMELS simulation suite, and to see exactly what I found and how it affects this higher dimensional galaxy property space, come by my purple poster later. Okay, thank you.
Hi, my name is Chad Popik. I'm a PhD student at Cornell working with Nick, and I'm working on SC effect and forward modeling. And so as we sort of learned, one of the goals is trying to use simulations and models to forward model against real data to learn information about astrophysics. But while it's equally as important to look at the uncertainties of the data in your model to understand how well you can constrain that, is looking at your uncertainties in your forward modeling. And so what we wanted to do was we wanted to, for the SC effect, which is a statistical measurement, it's very important to look at how you're modeling your survey. And so we compared using an HOD to model a survey to another survey or to another study, which was trying to model the same survey with different techniques to see in your final signal, what are the actual differences? And furthermore, in HOD modeling, what are other effects that would show up that could possibly explain why you might have, say, a difference between simulations and data? And what we found was that it doesn't fully explain the discrepancies that some people have already touched on, but it's definitely important and needs to be factored in.
That one's not mine, is that yours?
Chloe? Is Chloe here? No. All right.
Hi, everybody. My name's Christopher Rowe. Please call me Chris. I'm working with Professor Rob Crane over at LJMU in the UK. And we're working on looking at mass loading of low-mass winds from low-mass galaxies, and specifically the fact that if you look at the top plot at the top, with y-axis being mass loading, the individual data points show multiple different observations. It's a log scale, so there's a lot of disagreement, and observers fail to reach a consensus. However, simulations predict that this quantity for low-mass galaxies should be quite high, order of magnitude 2 to 3, so 10 to 100. So instead of looking at this directly, we're looking at it indirectly by tracking particle information, tagging it with its source halo, and then trying to map it to an observable quantity to have a look at this from a different angle. Thank you very much.
Hi, everyone. I'm Drew Zimmerman, fourth-year grad student at University of Florida. I work with Deshka and Narayanan. So what I want to talk about is that we get all of our information from galaxies that are observed pretty much exclusively from SCD fitting. And SCD fitting has a whole bunch of known systematic uncertainties built into it. And so the one thing you care about if you're modeling observed galaxies is getting your galaxy parameters right. And so we decided to try to approach this instead coming from a simulation perspective. So we have a whole bunch of the CAMELS simulations forward modeled with 3D radiative transfer that we're using as our training set to essentially create an SD modeler starting from simulations, take in photometry, any amount of photometry, which is different from classical machine learning models, always assume you have the same amount of inputs. Our model is designed to have any available input, And so spits out galaxy properties. It's doing pretty well. Come check out my poster.
Hi, I'm Haley Bowden. I am a grad student at University of Arizona, and I have been working on finding or creating new observables using the distances to a galaxy's nearest neighbors and the stellar masses. And we're trying to find observables that are more sensitive to different halo properties. So we use a deep neural network to go from this k nearest neighbors to the space of our halo properties. In this case, I am trying to look at the whether a halo or subhalo is falling, is currently falling on a more massive halo, or has been orbiting for more than half the dynamical time. And so this is the network we've created to do this. I'm currently working on creating a catalog of galaxies using the Gamma survey, the Galaxy Mass Assembly survey, and to look at the correlation between these halo properties and galaxy properties. Thank you.
Yeah. Hi, my name is Hanna, and I'm a PhD student from University of Seoul. And my poster is about the connectivity between the galaxy mergers and AGNs. So I first thought that it is quite natural that galaxy mergers triggers the AGNs, but there are lots of observations that reported there is no connectivity between the two. So we analyze the simulation data that we can access the full 3D information, and we found the connectivity between the two, and then we conduct the mock observation on the same galaxies by creating the mock observational images using the JWST near CAM filter, and we calculate the 4 morphological parameters, and we run simple machine learning to define the mock galaxy mergers. And this is the synthetic connectivity result, and this is intrinsic connectivity result. So if you wonder what is the result, please find me. Thank you.
Hello, my name is Elena. I am an undergraduate at Harvard University. My project focuses on predicting dark matter halo masses across redshifts, across 2 different hydrodynamical simulations, Illustris and Astrid. We use a graph representational learning, which just means that we only use the spatial data of the galaxies as part of a halo around a specific specified radius, and the graph neural network learns a graph embedding, which becomes an embedded vector, which then becomes a halo mass at some point. Something that we analyze is the feature dependencies of the graph neural network and our comparison model. And the graph neural network is actually very effective with only spatial data and JWST frequency bands, which is really cool because that means we need to know absolutely nothing. Thank you.
Is Jackie? Yeah.
So, hi everyone. I'm Jackie Yip from the University of Wisconsin-Madison, and then today here with this poster, I'm telling you that one can learn a great deal from the topological information of the data. And so the intuition for the application in LSS is that if you look at the picture over there, that different dimensional topological features refer perfectly to different cosmic structures. For example, 2-dimensional topological host refers to cosmic voids, and then 1-dimensional topological hosts are filaments, loops. And then for halo clusters, it's just 0-dimensional topological features. So essentially, we use this tool called persistent homology, a tool in topological data analysis, which is extremely flexible to extract these topological features from different scales. And then we build summary statistics from that, and then we carry out a Fisher analysis, which we find that for all these parameters, we're getting a substantial improvement in constraints. So come check out my poster later. Thank you.
Hi, I'm John Soltis. I'm a graduate student at Johns Hopkins University. I'm also going to be giving a talk on the same subject immediately after this. And then there's also going to be a paper on the archive tomorrow about this. So this is just a nice quick preview of this. But what me and my wonderful collaborators were working on was trying to estimate the mass accretion rate of galaxy clusters given just X-ray and TSE observations. So we trained a machine learning model using mock observations of clusters from the Millennium TNG simulations. We were able to get estimates of the mass accretion rates and uncertainties on those estimates. We compared it against the best available alternative, which was ultimately really just a function of the mass of the galaxy clusters. And there's a lot of scatter in the relationship between the mass and the mass accretion rate. And so what we found is that the machine learning model trained on this single simulation was able to do a better job than existing alternatives. We also then explored some interpretation of that. We found the uncertainties were reasonably accurate, that the model was not biased as a function of mass, and that it was also using asymmetry information in addition to surface density profile information. Thank you.
Hi, so I'm Jonathan Mercedes Felice. I'm a postdoc at UConn, and I have been running a filament extractor called Disperse on the CAMELS set. And the difference of running Disperse that I'm showing on this poster is that I'm actually running on the whole dark matter distribution instead of just collecting some type of sample or using different tracers. And so I've been able to run this for the whole CV and 1P set, and you can as well as on the end body and hydro runs, and I'm kind of just showing a lot of the variations that occur and the number of filaments in this plot here specifically as we change the parameters. and we have a really nice kind of correlation that as we increase omega matter, we get more filaments, and all of the different suites are doing really well, showing that with a negative correlation in sigma 8, but then we kind of don't have much information in the astrophysical parameters, but we do see some type of negative correlation there. So please, in the ASN2 parameter, so yes, talk to me about that.
Hi, I'm Juan Calles from the University of Valparaíso in Chile. The lightning review of this poster is basically that we have a pipeline that extracts topological information from Halo catalogs. And specifically, what it does is to extract different topological invariant quantities. And basically, what we want to do with this topological information is to map them to map the topological information into cosmological parameters. So at its core, this topological information is represented as a point cloud itself, and what we want to do is to apply different point-like architectures to extract these cosmological parameters, specifically using a deep set model or a point net model to do the regression problem to extract primordial non-Gaussianities amplitudes from the Quixote PNG Latin hypercube. So if you are interested in PNG or alternative summary statistic or different machine learning models that work on point clouds, please reach me.
Hi, everyone. My name is Juan. I am a PhD student at Tohoku University in Japan. And my work here is focused on finding a new way to study galaxy morphology. And the way we do this is using interpretable CNNs. So the main idea is you take the galaxy's broadband image, in our case 3 bands, from SDSS manga, so GRI, and we basically are able to predict the stellar mass, the star formation rate, and the age of the galaxy with spectra-like accuracy using photometry only. And on top of that, what we're really interested in is the interpretability side of things. So not only does it get the predictions correct, but we want to know why it's getting it correct or which parts of the images are the most important, which is kind of that heat map you see over here. So we generate these heat maps using SHAP values that tell us which parts of the image are most important for making predictions. In other words, which morphological features are tied to which physical parameters. And if you're interested in seeing the results of this and also how I plan to use this in simulations to kind of try to trace the physical phenomena that are causing these things, and also for cosmological-based simulations, please come see my poster. Thank you.
Okay. Hey, I'm Kai. I'm a student in Munich, and I'm just going to be giving a quick teaser to my talk tomorrow. So first of all, I would like... Oh, something went wrong here. So you will have to believe me. Okay. So we've seen this top plot in a couple of variations today, right? So we look at simulations, and the power spectra are different, right? But it is not clear that at these small scales, the power spectrum would be a very efficient way to actually look at the cosmological information for these non-Gaussian fields. And so we ask, is this really the full story, or can we look at this from an optimization point of view? Yeah? And so what we do is we train asymptotically optimal summaries for these simulations, and then also try to understand, okay, after we have trained and gotten these simulations, can we learn something about these baryonic physics models that enter these simulations from looking at the summary representation here. And we think that with very primitive ways of looking at this, we actually find some insight, and thank you.
Right. Hi, everyone. I'm Kentaro Nagamine from Osaka University in Japan. I would like to introduce our crocodile simulation series to you, which was performed by Yuri Oku, who's sitting there. And he's going to give a talk on Thursday morning, the first talk. And this was his PhD work. And our simulation features our custom supernova feedback model, considering the top heavy IMF and the variations depending on metallicity. And then we're performing various sets of simulations, varying feedback models with and without agent feedback, et cetera, providing data set to CAMELS. And we're already done with one PCV SP set. And we're now moving on to L50. So I hope you'll get access to it very soon and start using it. Later part of the poster, we also talk about metal distribution, gas fractions, and also IGM tomography, which is one of the focus of the PFS project, which will be carried out in Japan very soon. So we are probing feedback, close to the galaxy and looking at the H1 decrement, the laminar flow absorption. And then based on that, we're arguing that we can detect about 30% discrepancies depending on feedback models. Okay, thanks.
Hi, my name is Kun Hao. I'm a grad student working with Booth at Penn. So hope you are convinced by the talk this morning that this kind of works. Some people will call it a miracle. I would rather call it an approximation. The main difficulty of this work actually just comes from the simple fact that there's no analytical inverse function of something like exponential of x plus x squared. At least I don't know that. I just want to mention two possible follow-up of this work. One is because we can generate as many maps as possible. We want to explore like training more complicated and sophisticated models to extract all the information in a weak lensing field. As you can see here, that already helps with some initial tests. Another possible thing of this work is to push this to even higher resolution. And I think with that, we have to go a little bit further beyond this local transform. We probably have to like have some filter. Well, I don't know, but happy to chat.
Is Laura here? Is Laura here? No? All right, hi, I'm Lucia. I'm a postdoc upstairs. And this is a very funky project where I use the CAMELS SAM pipeline to essentially constrain or figure out how our misspecification of galaxy formation modeling affects the FNL parameter. So SphereX in particular is a space telescope whose entire reason for existing is getting FNL, which is a parameter that can rule out a lot of inflation models to one is the sigma. But the problem is it's completely and fully degenerate with two parameters of galaxy bias. So in this project, which I think is the first of anything close to this scale, we ran separate universe simulations that essentially changed the Santa Cruz semi-analytic model to really crazy amounts. And you might wonder, okay, how do your galaxy bias parameters change? Can we build priors from this? And the answer is probably yes. There are some selections of pure galaxy statistics that are very strange and very weird, and others where maybe we do have hope to have nice galaxy priors for SphereX. Thank you.
Hello, I'm Maya. I'm a grad student at the Australian National University, and my goal is to link the shape of galactic orbits in bulge and the stellar ages. So the orbits is something I have calculated mostly for a few types of potentials from simulations, but the age is the tricky part. So we are using SDSS5 Milky Way mapper, spectra, and we want to link that with astroseismic age. So I have used the Canon from Melissa Ness as a baseline, and the next step would be to train a bigger model that would be fine-tuned to finding the link between the astroseismic age and the spectra, but I think I need a little bit more data. So I would love to have a chat about that. It's still work in progress, so yeah, if you're interested, let's chat. Thank you.
Hi, everybody. My name is Max. I've been working on a project looking at intrinsic alignments, where if you have a high-level intrinsic alignments, it's kind of like a porcupine with satellites pointing in. And if you have a low level of intrinsic alignments, it's not a porcupine. And this affects your convergence, and we see that in power spectra. But we were curious what happens if you actually just measure galaxy shapes in illustrious TNG or a hydrodynamical simulation. Would this lead to some effect in non-Gaussian statistics, like peak counts or minima? So we propagate the actual shapes from galaxies in illustrious TNG all the way through to create convergence maps. We extract the peaks, and we find that there is no effect if you consider the ones that have intrinsic alignment effects versus the ones that do not. Thank you.
Hi, everyone. I'm Minsu. I'm a grad student at Penn working with Boov. I spent a lot of time thinking about how to improve likelihood-free inference, and this is a poster on work I did for dimensionality reduction. With a lot of math and NERSC I show that well-motivated linear techniques are optimal, it seems. And so these new techniques that we propose, as well as some tips and tricks, each provide like 40% increase in the figure of merit in the omega matter and S8 figure, which is pretty great. And it's 2024, so you might ask, how come neural nets are not better? It seems like if within your simulation suite, the parameter response is linear, so that's to say the response really is linear or your prior is really small. This is robustly the case. Another thing that this is useful for is if you want to do beyond standard model LFI, this seems pretty useful. And if you want to hear more about cool math in this corner, or want to hear me rant about mutual information for 10 minutes, please come by my poster tomorrow.
Hello, everyone. My name is Niyantri Krishnan. I am a post-baccalaureate intern working at Argonne National Lab with Dr. Nesa Ramachandra and Dr. Katrin Heitman. The project we're currently working on is constraining early dark energy models with power spectra emulators, which uses a Gaussian process emulator to investigate power spectra in an early dark energy cosmology. The early dark energy model was introduced as a modification for the lambda-CDM model to resolve the Hubble tension discrepancy. And we ran holdout test runs to test the accuracy of our model. And we found that at large scales, the residuals are close to 0. And at small scales, there's slight discrepancy. We also ran several MCMC samplings and Fisher information and sensitivity analyses to understand the relationship between these parameters and constrain them, and we were able to achieve tight constraints. Thank you.
Hi everyone, my name is Parker Thadari. I'm a 4th year PhD student at Stony Brook University, where I work primarily on blending with Anja van der Linden. Blending is any time the flux from a long line of sight can be attributed to multiple objects. It's an important systematic that we need to take care of. It affects your cosmology and photoz's. Some work has shown that if you don't take care of blending, it can lead to a 2 sigma shift in your inferred S8. So if we can capture all the blends, you might be able to resolve some tension in S8. Our technique is just using a catalog that's been labeled. So you have colors, you have size, pass it into your favorite machine learning algorithm, which for my case is random forest. And you can see how you do. We're able to catch a decent number of blends at a small fraction of the cost of the sample. And we're now focusing on the second half of this is implementing this into cosmology with cosmic shear. Cosmic shear today is quite complicated. We need to be careful that we're not making strict selection effects and that we can mitigate those. So I can remove blends, and I'm going to see how does that affect cosmic shear. If you're interested in blending, cosmic shear, and any other systematics, talk to me at my poster.
Hi everyone, my name is Roman Knight and I'm from CAMELS University in Bratislava, Slovakia. And together with my PhD student Filip Janak, we worked on training a probabilistic random forest to calculate or to estimate the amount of H1 gas in galaxies. We also performed some performance tests to evaluate the efficiency of our model. And we trained our model on alpha-alpha catalog, so the sample of galaxies which contains the information about the amount of H1 gas in these galaxies. And then we can use our data to evaluate or estimate the amount of H1 gas or H1 deficiency in galaxies. We also we tested dependencies, how the amount of H1 gas changes with various environmental properties. So for more information, check our poster. So see you tomorrow. Thanks.
Hi, I'm Ryan. I'm a PhD student at Liverpool John Moores University, working with Rob Crane. So my work focuses on investigating the driving factors behind the scatter observed in the circumgalactic mass fraction in simulated environments at fixed halo mass. So previously, if you wanted to do something like this, you might take a Spearman correlation coefficient, but the problem with that is that it only tells you the relationship and the correlation between the individual feature and FCGM itself, so it might miss some important things out. So what we do instead is we train an XGBoost model to predict FCGM. And then once we can do that, we can then use SHAP analysis on it. So that's a method that lets you retroactively determine feature contributions in a machine learning model. And we can do that on a halo by halo basis. So instead of one individual contribution, like a correlation, we can build up like a macroscopic, like mass bin range, feature importance and like relative importance between a set of features in driving FCGM. Thank you.
Hello, I'm Sagan Southern. I'm a student at the University of Connecticut, and my project right now is just taking the Simba model and remaking it with the Swift hydrodynamic and gravity code. All right, so my job right now is mainly just tuning the model, right, so that it matches better. The main goal is to have them match as close as possible, with the eventual idea to have a complete CAMELS suite with Swift Simba, right? And so the idea there is there's a lot of interesting machine learning applications we can use for that, particularly with questions of robustness, like what happens if we train a machine learning model on Simba and then test it on Swimba, as we've taken to call it, and vice versa, right? So those sorts of questions are those that I'm intending to answer over the course of my PhD. So yeah, come ask me about that. Yeah.
Hi, everyone. I'm a first-year grad student from UIUC. My name is Shui Ling. So as was shown by Biwei, correlation between hydro spectrum and dark matter-only spectrum is very close to 1. So the ratio between them seems to be the key for feedback. So In and I was trying to train a VAE model to find a disentangled latent representation for all the different code in the CAMELS, and it turned out we get quite good reconstruction within the latent variance, and our title is actually aligned. We get a 2D latent space to encode all different codes, so one ring each hand. Also, from the cross-correlation, we find basically there's no correlation between latent and cosmology, and there was 6 parameter in the Sobol 28 feedback parameters that basically dominates the latent contribution of feedback. Any comments and suggestions will be appreciated. Thanks.
Hello, everyone. This is Sultan Hassan. I'm a Hubble Fellow down the road in NYU. So this is mainly about LLMs. So this work has been done in a fellowship within Kaggle and Google community. So we know that we have a huge amount of literature now, and it's very hard actually to do everything by manually and looking at the search in Google. So probably you really need to automate this process. So the basic idea is that LLMs are great. They answer questions, but when you fine tune them to domain specifics, they result in great accuracy. So the basic idea, you go to archive, you generate your data set you wanted, you use some tools to try to generate conversation style data set, and then you fine tune the model. So the model is called Cosmogema, and this is just to show the model is able to answer multiple choice questions and also brainstorm ideas, which is, I'm very interested about how to solve, like to pick up other projects, and these are the QR codes for the full release of the GitHub and the app. So please try it. Thank you.
Hello, hello. I'm Tree. I'm from Sierra Northwestern University. I do a lot of machine learning, but one of the things I'm most excited about is to build generative models, forward modeling, like emulators, whatever you call them, for simulations. And let's say one of the most common way that you study galaxy formation is you either run a hydrosim. You don't always have the time or the money to do that. But you can run an n-body simulations, dark matter only, and then try to paint the galaxies on top of that, right? If you want to learn how to paint galaxies onto dark matter halos, come to my talk on Thursday. If you want to generate the halos themselves, generate the merger trees themselves, you should come to my poster. So merger trees are, I would say, almost as complex as generate the entire simulations, because you have to keep track of over every single snapshot that you have, right? You have to measure the properties of the halo, you have to measure the merger rate, how they merge together. Basically, this poster is we develop models, graph-generated models, which is basically just a bunch of transformers to do that. Can you actually do that? Come to my poster and find out, but the short answer is yes.
Hello, I'm Zev. I'm an undergraduate at the University of Maryland with Dr. Benedict Diemer, and my project is on using a dynamical definition of halos. So the traditional definition is to use an overdensity sphere, but Dr. Diemer has been working with some other people to create a dynamical definition. However, the way they determine if something is orbiting and actually belongs to the halo or is infalling is either very computationally expensive or is rather slow, or is just less precise. So what he asked me to do is use a machine learning model, and I chose XGBoost And then I trained that on a phase space parameter data set from many m-body simulations, and then examined it in the phase space of our model and in the density profiles. And we find that it is very accurate in regions of high density of orbiting particles as well as infalling particles, as well as very closely matching the produced orbiting and infalling density profiles of the halos. In addition to the model that creates very high accuracy classifications, we investigate using shaft values the importance of various parameters. So we show that in addition to being faster and more accurate, we now have a model that can give more physical insight. Thank you.
Hi everybody, I'm Zsofia Chrobakova from University College London. So in this project, together with my colleagues, we developed a deep learning algorithm for detection of warped or edge-on galaxies. So you can see here what is the galactic warp. So it's this bending of the outer edges of disks. This is present in spiral galaxies, and it's a very common phenomena in the universe, but we don't know what causes it. So in this project, we want to study what are the relations between galaxy properties and environment and warping, if we can find out any information that could help us understand what causes this phenomenon. So we trained the YOLO algorithm to look for these nice edge-on spiral galaxies where we can then measure the warps. So we apply this on the SDSS data. In the future, we hope to be able to apply it on the Euclid, where we are going to have a lot of new galaxies where we will be able to detect the warp. Also, then we have this UNet-inspired algorithm where we segment the image, extract the galaxy, and here you can see an example of a warp calculation. So for more information, come check out my poster. Thank you.
Thank you so much to all of you. Let's give a big round of applause to everyone. This was wonderful, and the timing was impeccable, and thank you in particular for all those with the first names towards the end of the English alphabet for standing for so long. Okay, so we will continue with a couple of talks now. John Soltis is the next.
All right. So I'm John Soltis again, and this is the same thing that I was talking about before. So we were working on a machine learning model to estimate the mass accretion rate of galaxy clusters. So first, just a little bit of background. I'm sure all of you are very familiar with this already, but galaxy clusters are the most virialized objects in the universe. They're very large, so they're very sensitive to cosmology. They're also about 15% hot ionized gas. So that's what we're going to be focusing on in our observations that we're using. We're going to use X-ray and TSE observations, which probe that. And really the thing that we're interested in with galaxy clusters is in their formation history and in their merging. So galaxy clusters, like everything else in the universe, are a product of hierarchical structure formation, so they're constantly eating their neighbors. They're taking in smaller galaxy clusters, taking in galaxy groups, taking in gas and dust and dark matter from the filaments, and the result of that is that they're getting churned up and in various states of disturbance. And this disturbance is visible. So in this image that's very low resolution and also normalized, I'm showing the highest mass accreting cluster in the MT and G data set in soft X-ray. And you can see that it's not a nice circular galaxy cluster. Instead, it's very extended. You can also see what looks like a little bit of substructure. So it's a very disrupted object because of its high mass accretion history. And because we're interested in this mass accretion history because of how it correlates with other properties of galaxy clusters in cosmology. So like I said, galaxy clusters are sensitive to cosmology. If you estimate their masses, you can count galaxy clusters by their mass and use that as a probe. Unfortunately, mass estimates can be biased by the mass accretion rates of galaxy clusters. And so this is sort of a confounding variable for cosmological analysis with galaxy clusters. It's also correlated or related to different astrophysical processes in galaxy clusters that you might be interested in, like galaxy evolution or maybe AGN behavior. And finally, if you had all of the mass accretion rates for all of the galaxy clusters, you could use that as itself as a probe of cosmology. So if we were able to measure the mass accretion rates of galaxy clusters just from observations, that might be very useful. And so that's what we wanted to test and see, is are we able to do that sort of as a proof of concept? And so naturally, we turn to machine learning because the relationship between an observation and some small intrinsic property is sort of non-trivial to figure out by hand. And so again, we started with X-ray and TSE observations. We trained a supervised machine learning algorithm that was a combination of a convolutional neural network and a normalizing flow. We did that because convolutional neural networks are very good with images. Normalizing flow model allowed us to get uncertainty estimates because it's approximating a distribution. Basically, what it's giving us is the probability distribution of mass accretion rates given the observation that we're seeing. And so, yeah, this is what we end up with after training on Millennium TNG, which is a very large hydrodynamic cosmological simulation. Thank you to the MTNG team for giving us access to this. We had about 4,000 unique clusters. They were all at the same redshift. So in this sort of preliminary experiment, we weren't probing, being able to test different redshift evolution of galaxy clusters. There we go. So did the model work? The model worked better than what we had before. So yes. We were comparing it to a fitting function from Benedict Diemer's paper in 2020. This fitting function, when you're using only one cosmology, just reduces to basically being a function of mass. So it's saying, given the mass of a galaxy cluster, what's the mass accretion rate? Like I said when we were talking about the poster, there's a lot of scatter in this relationship. So that's what the red distribution is. The machine learning model, and this is not like a hyper-optimized model. This is just sort of a first attempt to see if it's possible. You can see that it does quite a bit better than that, almost a factor of 2. The number that I quote here is that for 68% of the clusters in our data set, you can constrain the mass accretion rate to within 33% error. And this is true even if you only use a subset of the observation types that we have available. So normally we're using X-ray and TSE together, but you can also use just X-ray or just TSE, and you get slightly worse but similar results. So the other thing that I talked about is we wanted to do this normalizing flows model because we wanted to get uncertainty estimates, not just a single estimate of the mass accretion rate. So then after we did that, we wanted to test how accurate are these uncertainties. And so the way that we tested that is the model that we have, basically you're generating a series of sample mass accretion rates given an observation. And so if you generate enough samples, you can get a confidence interval from that. And then we asked, how often does the true mass accretion rate that we measured in the simulation fall within the confidence interval? And what we found is that it's a slight underestimate, but it's still reasonably close to what we want. And again, it doesn't really change that much when you use only X-ray observations or only TSE observations. Finally, and I didn't mention this, but again, because galaxy clusters are a product of hierarchical structure formation, there's many more small, like low-mass galaxy clusters in our data set than there are high-mass galaxy clusters. And so because of this, we wanted to test and see if there was a bias as a function of mass in our data set. Now, we kind of suspected that there wouldn't be because, again, mass isn't necessarily that informative. But what we found when we tested our model was indeed it wasn't biased as a function of mass. Unfortunately, and sort of not unexpected, it was slightly biased as a function of the true mass accretion rate, which, again, was also not a super uniform distribution. So there are some very extreme mass accretion rates that weren't well represented. And in those cases, it's slightly biased, but still better than you'd get from guessing. And then finally, we wanted to test how to interpret this model. So we actually spent quite a bit of time looking at this. But the thing that we ended up taking away from it is that if you decompose the images into a radially symmetric image that I'm generating using a fitted radial profile and just sort of a remainder which represents the asymmetry in the substructure in the cluster, what you find is that the machine learning model is clearly using both components. So this kind of goes back also to what we were saying before about the mass, because the mass information maybe is also in the symmetric component. But what we're seeing is that it's using sort of both the asymmetry and this radially symmetric component. The way that we actually tested this is that we gave the model just the symmetric only components and then saw what kind of mass accretion rates it predicted for that. And there we found that it systematically underestimated it. Yeah, and that's it. I think I went a little bit fast. But
thank you. Let's take questions. Please.
lovely talk. I was curious, did you test to see how kind of robust your mass estimate for inflow was for, like if you have different feedback?
So we only used a single simulation. So that's definitely a limitation of this, is we have sort of a single set of astrophysical assumptions that we're working with here. So sort of the next step that we would do would be to look at varying assumptions like feedback and seeing how the model performs when you train it on one and apply it to another, and then also how robust can the model be when you train it on sort of variable assumptions. But so the short answer is no, but we will.
Ken.
Can you separate the spherical accretion versus filamentary accretion from your estimates?
I haven't looked into that. Looking at the observations by eye, it's not obvious to me where the filaments are in the images that we're feeding to the machine learning model. But that would definitely be interesting to look at.
Because
right now, yeah.
Presumably your anisotropy that you mentioned is related to the filamentary accretion from the larger scale filament, right? And
Yeah,
also,
that or just related to sort of major mergers. But yes, yeah, definitely. I think that would be interesting to look at.
And also how that relates to the dark matter accretion rate that you measure from in-body simulation would be also interesting to compare.
Yeah, no, I agree.
Okay, thanks.
Any additional questions? Yeah, Haley.
Hi, very interesting talk. I'm curious if adding, I guess, additional observables would, whether that gives you more information, like if you've used, I don't know, some kind of optical clusters.
So that's also something that we're very interested in doing, sort of moving forward. I think I mentioned it on the bottom very briefly, but sort of talking about like gravitational lensing or spectroscopy from galaxies within the galaxy cluster, just additional information modes, I think definitely would improve the constraints and also might be a nice way to try and get around sort of tricky assumptions that we're not sure of in the simulations.
One last question, if there are any. All right, let's thank John again. And we move on to, I think, what is one out of only 2 remote talks that we will have during this meeting. So, Ben, are you
Yes.
online? Yeah.
Can you hear me?
Yes, we can.
Okay. Yeah. All right. And does that appear to be mostly like the correct presentation in my browser?
Yes.
Okay. Thank you. Yes. All right. I'll start. Thank you for letting me give this talk, and I'm very sorry I could not be there. I will be presenting work by 2 students who either are or were undergraduates with me, Calvin Adams and Caleb Ogle. And our team also includes the names along the bottom, including Matt Ho, who led us down the road of using deep sets, which I'll get to. So these are these 2 students, and they're both writing up their results in publications. Calvin Adams is applying to graduate school this year for next fall, so look out for his name. And Caleb Ogle is at UW Milwaukee Physics now. So what is our motivation? It is to develop a new type of neural network that can infer halo properties across multiple telescopes with heterogeneous data types. So for example, some data is in an image format, such as X-ray images, radio mapping of neutral hydrogen, etc. Other data types are data sets that are not structured in an ordered image, where the order of pixels matter, and the data can be contained in a list, such as a galaxy catalog, data containing galaxy masses, star formation rates, magnitudes, redshifts, etc. I want to take a minute here and emphasize the importance of the targets that we are trying to infer are centering on galaxy groups. This is the halo mass range of 10 to the 13 to 10 to the 14 approximately. That is in particular important to understand because these objects have an outsized impact on precise cosmological parameter estimation via their influence on the matter-power They are observed to have possibly moved many of their baryons outside of R500C, as we've seen from talks already today, and they're more numerous than massive clusters. Their impact on cosmic shears is the largest of any decade of halo mass. Therefore, determining their precise halo masses as well as baryonic gaseous distributions is essential. So this is our approximate outline. So I'm going to move kind of fast here and talk about Calvin's work with a CNN that he has developed and that ingests a lot of data from what we have used for now is Lester's TNG 100 and 300. Notably, there's X-ray, wideband images, narrowband images where you can have an individual line. Different each one 21 centimeter base data, which we don't forward model as much, but has different moments of column density, velocity, velocity dispersion. So the CNN architecture is based upon previous work by Paco and modified by Naomi Gluck to ingest images of galaxy halos and has been further modified by Calvin to take many multi-channels, multi-wavelength images from different potential telescopes. And it is a moment network outputting the mean and the standard deviation of the posterior distribution. So I'm going to flash a couple results here and then move on to deep sets. But this shows kind of the coloration of the halo mass, which is also plotted, showing the performance of, on the left, one channel, H1, in the middle, multiple X-ray bands, and then combining it together. And what's kind of more dramatic is when I show F-gas here. And on the left this is actually a statistic that is non-monotonic. It's actually lowest at the intermediate halo masses in Lester's TNG. And this is an interesting test case. So one radio channel on the left adequately infers F-gas. The X-ray channels do better overall. You might expect that because there's more hot gas that is traced by X-rays. But combined, H1 radio tracing cool gas and X-ray tracing hot gas provides better inference overall for the gas mass and hence the gas fraction. So now we're going to move on to deep sets. There are a couple important contrasts. First is that in relationship to the relation of the objects to each other does not necessarily matter. You can see that at the base level, think of, instead of a grid of pixels, a series of points, which may be applicable to a point cloud. Here, the point cloud is individual galaxies. So their order does not matter, and the numbers can vary, but we are working on galaxy groups and clusters with multiple galaxies. So the formalism is to create a function that operates on a point-by-point or galaxy-by-galaxy basis, represented by the phi operator here, and then sum them up and then work on them in terms of cluster by cluster, the basis, the row operator. And the network here is on the right. I want to jump to some results here. Caleb has worked with the Lester's TNG 300 data sets, and he has evaluated the moment network in both in terms of RMS scatter and the R-square statistic. I won't have time to go over every result here, but one that is a little bit surprising is that a small amount of shift in the position, this blue one here, is actually degrades the performance by quite a bit. But overall, it's quite good. But what we are trying to get to, and I have maybe a couple minutes, is the combined network. So the networks are optimized using Optuna, an Optuna optimized hyperparameter search. So the two networks I discussed up to now output latent vectors that are combined, and you can ask me more about how that is done later, into a final layer. And then the outputs of the moment network give the mean and the dispersion of the properties. So this is my second to final slide. So the blue results show the galaxy statistics from deep sets, the performance of that set of the network. The red results use gas constraints. These are very short X-ray mocks for 250 seconds, similar to E-Rosita ERAS-1. And then the black shows the combined results. And one thing that surprises me is that the X-ray exposure time does not really improve. You can, I don't know if you can see my mouse, but you can see in the upper level of that table, short exposures do quite well, and increasing the X-ray exposure time does not matter much, at least for M500C. And then Caleb and Calvin have worked together. They've worked very closely on this, on inferring gas fractions inside different radii, different fractions like R500C or R200C, and further out. And here, most of the information comes from the gas-centric CNN, but adding deep sets does find better cases, and F-gas is more gas than stars. So I'm going to summarize my point here, and emphasize that this work has been done by two very talented undergraduates who work closely with each other, and have not been afraid to reach out and ask questions amongst Brian Pasters and the CAMELS collaborations. So I leave their contact information here and talk about, leave you with a future direction of looking at other simulations with more groups, such as the CAMELS 50 megaparsec simulations, etc. Thank you for letting me give this talk.
We have time for a few questions. All right, yeah, Simeon.
Yeah, hi. Can you hear me, Ben?
Yes, I can.
Great. Is it only for clusters, or can you go all the way down? Right? Can you do CGM things like what we used to do?
Well, this is absolutely a CGM-centric investigation. I'm interested in groups. Obviously, Calvin is working on Illustrious TNG 100. So you can see that the halo masses here. I don't know if you can see I'm pointing to the purple part of
yeah, we can see the cursor.
Okay. Yeah, so gas fraction. I'm very interested in that. And things become more complicated there. You have more H1 in the halo. The cool phase, 10 to the 4 Kelvin can dominate. And X-rays, you will not observe individual X-ray halos. You have to stack, like Erwin's talk this morning, or you have to go very deep, and it's just too expensive to do. So yes, this is very applicable to the CGM.
Thank you, Ben. Let's thank Ben again. Okay, so now we have the discussion of the day. So Nick and Anna Maria can take the stage.
So while you're waiting for us, we put out a poll. Hopefully you guys saw it. Hopefully it made some of you angry.
It's very exciting. The results are
happy or sad. Meant to invoke some emotions, so there'd be discussion. Let's get it plugged in. And while we wait, let's just say let's thank all the speakers.
Thank you.
For the entire day. They were our motivation for this, so we thought this would be a good way to, further discuss some of the things that came up. And I will get out of the way. Take it away.
Okay. All right, so the numbers are shifting as we speak. Okay. So Nick and I emailed a list of 5 questions that hopefully will help us engage in conversations. Questions are the tensions between simulations and observations. Another question about the generation of cosmological hydrodynamicals. This one has a clear winner, I believe. small scales. Is it worth it? I think that has a clear winner and winning. The S8 tension. Okay. Not concerning is closing. Never mind. I believe that the last question, which is the broader, will the broader community
Save that one for
accept
last.
ML? We're going to save this for last,
Yeah,
but
we'll save it for last.
kind of evenly split. So, yes, that is emailed to all of you. Yes. If
Exactly.
it's sarcastic,
Exactly.
Nick thought of that one. Okay.
So for this first one, we have a pretty good split. Does anybody want to speak for the concerning side? So anybody who voted for concerning, does anybody want to express their concerns?
Do you mind giving us a list or examples of these tensions?
Me personally, yeah, sure. We saw several of them today. So Boriana showed some interesting ones. Alex showed some interesting tensions. We saw some from Irwin as well with the X-ray. So, just showing that even with a broad range of CAMELS simulations or other simulations that you can't really fit some of the gas data that these simulations aren't tuned to.
I think if you use those successful simulations that fit the gas data, they kind of underproduce stars in massive halos. So that's the tension. I think that's the remaining tension.
Or you could phrase it another way. If you fit the stars, which most of the galaxy formation simulations do, you don't quite get the gas right. At least that's what it looks like.
But that's not what Alex showed. That's not what you said. I mean, you said that you are able to reproduce the stellar mass function and all this.
Alex showed one simulation that was able to do a lot of things, but there's still things that it actually is going to be tested on that Alex and I have been emailing about.
It's not published yet.
Can I just ask the question, the way we are comparing observations and simulations, are we confident that we can decide whether there's tensions or not? I wonder whether somebody has an opinion.
Yeah.
I mean, are we really comparing it apples to apples? I don't think so.
Right.
There's no error bars in any of the plots.
Boriana.
Well, no, there are. There's definitely there's observational error bars for sure.
Boriana. Sorry.
We'll go Daisuke, then Boriana.
I think that's probably part of the value of the mission is that it's teaching us whether the modeling is done properly or that observations are interpreted or systematics controlled properly. One or the other. Either way, it's very useful.
Boriana?
My take is basically almost the same. I mean, I think that there are probably ways in which we can improve the way that we are doing this apples-to-apples comparison, but ultimately we should have a coherent picture between, say, if we're using n-body simulations with gas painting or hydro simulations and that are small boxes or large boxes or high resolution or low resolution. So I think it's worth doing all of these things and trying to make sure that they tell the same story.
And I think there's a push in these comparisons to do sort of a full forward model towards the observations. That way we're not messing around with reinterpreting error bars and things like that.
Lucia, did you have your? Oh, I apologize. Alex?
I was going to add that for the KSC comparisons that we showed against Flamingo, I mean, there was real reluctance among our co-authors to publish this unless we fully showed that we had not had some sample selection. So we could perfectly reproduce gas-Gatsy lensing, the clustering, the halo mass. We could change the distribution under the hood. We could change the colors, and that result did not move.
Okay.
There's still some other ones.
Anyone want to talk
Not
about?
concerned.
Who is? Does anyone want to volunteer? This is supposed to be an anonymous poll, but anyone who is not concerned, go ahead, Chris.
I interpreted this as like, I think we know that there's tensions, and I think we kind of maybe know why. So like, in terms of like concerned, I would say I'm I'm not concerned about the known things that don't fit. For example, you know, going to higher resolution, larger box sizes. There's like clear axes of merit that we know certain simulations don't match observables, but we know kind of the solution. We don't know how to get there, but we know, you know, sort of, you know, how to approach some of these issues. So that's how I interpreted not concerning. And yeah, it sounds like I was the only one.
So what are the solutions?
Well, I think, yeah, so some of the painting, baryon painting that we've heard a lot about today, but using, you know, higher resolution simulations to do that, and more sophisticated ways of modeling covariances, for example. Happy to chat more afterwards when I'm not on the spot.
Sure.
I think I'm not concerned, but I think concerning is just the wrong way to think about it, because I guess I would ask, what do we expect? We keep moving the goalpost of what is consistency or lack of tension every time we have a new experiment with higher precision, or we want to probe new nonlinear scales or go down in scales. So the goalpost keeps moving, and so obviously everything's going to break, and there will always be tensions. So it's just part of learning physics, right?
Yeah, but don't we want, I mean, we want to build towards a predictive, right, model of galaxy formation, right? Isn't that the goal? Isn't that a goal? It doesn't have to be the goal.
I think that is like the goal of galaxy evolution as a field, or galaxy formation. So I don't think we should be concerned that we're not there yet. Like, the field's not dead. That's good, right?
Everyone retire and go home.
I guess that's the exciting side. Ben?
Reply to that is, if we don't know, if we can't fit everything with the existing data, maybe it's harder to justify spending $100 million or $1 billion on the next thing to push the tensions further, if already with existing things we're not matching. I know, it's not my money either. I guess it is. I guess it is my money if I pay U.S. taxes, when I pay U.S. taxes. But yeah.
Paco?
So there are other fields that people have been trying to break, like particle physics. They have been trying to break the standard model, and they haven't managed.
And it's like super boring, right?
Yeah, but
for us, it's like super fun.
To be fair, no one selected boring. So, point made, yes.
And I guess hopefully for those of you in the magenta color are aware now. Or not.
All right, shall we move on?
Yeah.
This one has a clear winner. The next generation of cosmological hydrodynamical simulations should go bigger, higher res, refined subgrid physics, or fast painting methods. So there's a clear winner of refined subgrid physics, but I believe this would make a nice conversation given the percentages. So would anyone like to volunteer their position? Yeah, Daniel.
To be honest, I don't remember what I replied to this one, because I think all of them are necessary. So maybe it's the politically correct, maybe too much answer. So yeah, I guess, yeah, galaxy evolution, we want to understand the physics, so we want to refine the subgrid physics, make it more as physically predictive as possible. That will help reduce errors and improve inference, but we will probably never fully, absolutely 100% understand everything, so we will always have to marginalize our uncertainties, and anyway, we have to go bigger to help our cosmology friends. Yeah, and we'll need some kind of painting method, because we'll never be big enough, probably, a high enough resolution. Anyway.
Daniel is the mayor.
Yes. So you probably wouldn't be surprised if I told you when we initially put this question together, there was an all of the above, but we didn't want that cop-out. We wanted people to discuss. If you could only pick one.
Which one?
Which one would it be, Tom?
I want to take a strong position for the fun of it.
Okay, good.
Obviously, higher resolution, right? I mean, because current galaxies, I mean, what we know about galaxies, their typical scales are much smaller than what we have in the simulations. So the simulations are so far from the thing we're talking about. I mean, the scale heights of disks, the scale of molecular clouds, inter-arm separation, all these things are so much smaller than these current simulations. Obviously, we have to go to higher resolution. It's not that interesting to have other subgrid physics on scales that are not commensurate with the object we're studying. And I often say it's like taking pictures of people, you know, but having pixels bigger than their faces.
Anybody want to disagree with that or second, or go ahead?
It depends on your bank account, I guess.
Very good. I'm not against it. I would like to have high resolution simulations as well, but it's just a drawback or to rethink it that current models is built on a certain resolution. If you want to go to, let's say, stellar resolution and things like that, we have to also refine the Bayesian models. So that is like going hand by hand, things like that. I would say it would be better in this way, not just, okay, just go to high resolution and with a model that which don't have the capability to resolve all those physics, right? So that is my thinking regarding to that. It's not against high resolution, I would say.
Let me also say, all the progenitors of all the objects you're studying, we know were smaller than your resolution limit.
Yeah, I agree
Another
with
reason
that.
why
Yes.
you know, you clearly want to go there, given you have high redshift data.
Those of us that don't work with the space that much, so like, what is the current resolution for, I guess, some of these hydrosims, but also what is the reasonable goalpost for resolution that could be obtainable in the next decade, I guess? Like, if anyone knows.
Roman wants us to type this into ChatGPT. Include MHD. Oh. Okay, we can. So clearly it hadn't had time to read our poll yet because that wasn't an option. Any answers to from the simulators?
What's our goal?
There's a whole row of them right here.
Yeah, so I would say that even with these flagship large simulations that you can only run one of, galaxies are barely resolved, depending, of course, on what volumes you want to simulate and how many models. But I would say, yeah, in that kind of ideal scenario of large volumes with many models, certainly we're extremely far away from like really resolving galaxies. So there is tension between all of these things.
Then I guess going into the opposite regime, if we wanna learn more about the physics of galaxies, we can focus on only a few ones and use like zooming simulations of only a few galaxies. We can achieve much higher resolution and detailed physics, but then that doesn't help us learn about sort of the large scale structure and connect with cosmology and so on. But yeah, so I guess current resolution go from, I don't know, subparsec resolution in some idealized models or very high resolution zooms, all the way to, I guess, many kpc very low resolution for like giant volumes. So always this trade-off of like volume and resolution.
Yeah, maybe. I guess the question is, I think as we go to smaller scales, there are small particle physics kind of thing, like for example, PIC simulations. The plasma physics simulation will manifest itself, all these little instabilities that you see in plasma fusions and collisionless shocks, they will probably have some impact on setting viscosities of the gas on large scales. So those are the subgrid physics that we really need to get our handles on. And those are small scale particle physics type simulations that we don't really know all of the instabilities. I think what we're learning is that we're finding all these more and more instabilities that might do that impacts those macroscopic features like viscosities and conductivities, including high beta plasma, which is rarely realized in terrestrial kind of or even solar experiments. So those are the big tensions, is that we don't really have handles on the small scale plasma physics on cosmological scales. So that's one big area that we really need to gain better insights, and we can use these the observations to learn more about it. Or maybe those plasma physics on cosmological scale is something that we need to bridge the gap. Those are much smaller than just galaxies.
Another comment on kind of pitting high resolution and subgrid physics against each other. I would say that I mean if we push on the resolution, but we have bad physics, as Daisuke just said, I mean that's not going to get us to where we want to be. There is some hope, though it's hard, I think, to develop subgrid models without pushing on the resolution. Those subgrid models will somehow capture those unresolved scales yeah, I think the community is working on it. I'm not sure yet to what
the scale height is 100 parsec or 50 parsec. You have a kiloparsec resolution. Isn't that by definition no subgrid model is gonna model that?
Then I think maybe the question is there any information on the resolved KPC scale that will allow you to essentially extrapolate to down to the scales that you don't resolve?
Right, the dwarf galaxies we care about, they have 200 parsec, the whole extent
right.
where the stars
but maybe there's something about the resolved conditions around that dwarf that you can somehow capture with some subgrid.
Good. Let's we'll move on. Thanks.
Okay. This is kind of related. But this is a very clear winner. Given the issues on going small, is it worth it? Yes, clearly wins.
This is in the context of cosmology. Sorry.
This is in the context of
Put
cosmology.
this in context. Yes, we had Simeon.
I want to very strongly disagree with the winning, the winning option, because once you go nonlinear, all the modes get correlated. So there actually aren't as many modes as you think they are, and I think a better way to think of it is to try and estimate the real space density field rather than the Fourier space density field, and to think about where the halos are and what we can learn about structure formation from the location of halos or the location of filaments. Or indeed the location points.
Okay, good. Yeah, no. So yeah, there's not k cubed more modes, I agree. But there's still more modes. Well, that's the, I mean, so is it? Oof.
I mean, I'll agree with Simeon by adding that there's also a lot more parameters. So, with galaxy redshift surveys, there's some anecdotal evidence that you go a factor of 2 or 4 deeper and you gain 20%, because most of that information is absorbed by your nonlinear bias parameters. So it's a very interesting open question. I mean, one way or the other, we're going to analyze the small scale modes. Whether it's to explicitly just learn about the astrophysics or to do what seems logical, that you marginalize over the astrophysics and extract a bit more cosmology. It seems logical, but I'm not sure the risk reward is worth it.
I think that it's kind of tied to the second question, but given that we tested the universe pretty well on large scales and we find this very strange situation where we keep agreeing with lambda CDM but don't know what dark matter and dark energy are, there are very clear ways to test for signatures of dark matter on small scales. And I think we would be remiss to just keep going for large scales and not try to find some other way to break.
Well, say it. Shut up. Somebody new.
Yeah, so just to point out, even by going to small scales, so there are observers at the modes, wave modes that we have for large scales, which do get affected by introducing more small scale physics. For example, I do high redshift stuff, so for the 29 center signal at the epoch of ionization, your resolution and the kind of small scale physics you resolve do affect, because they compound together for the things like power spectra or bispectra, and they show up at large scale. So even for things that we do care about now, they will change if could use small scales.
Yeah, agreed. It's also, are we going to learn about cosmology with 21 centimeter, or are we going to learn about astrophysics? Anyways, that's a different topic. We had some hands over here first. We had Paco, and then we'll go Boriana, and then we can go Daisuke. Paco.
Yeah, so I maybe disagree with Simeon a little bit. So this is not. Yeah. So I mean, I don't know. Maybe I'm too old now, but I remember when I was a student, the typical argument was that you should not go into the one halo term because all the orbits are chaotic and there is no information there, right? So that's why I always was tell that you should use the power spectrum and K.2, 0.3, and that's it. It's like it was very clear that there is no information. I think these days, people has done with a lot of different simulations that this is not, and we know that things like concentration or the accretion rate, all these things correlate with omega matter. So, from the experience that we have with CAMELS, we know that we can go to K of 100. There is still information there, robust information. Some crazy people can say that you can even do cosmology with one galaxy, that maybe, but yeah.
Brianna?
I guess just wanted to say, I actually voted for the forget cosmology astrophysics answer here, and it's not to say that I don't care about cosmology. I still really like it, and I still think there is a lot to do in many, many different ways. But I do think that for a lot of these problems, it is actually really fascinating to try to understand the astrophysics and to try to put together a coherent picture. And I think that will also help cosmology eventually, but maybe we shouldn't be focusing ourselves so much on the cosmological application, but first think about sort of the story and whether that makes sense astrophysically, and then apply that to cosmology.
Great, thanks. Okay, Daisuke and then Ben.
Maybe I think for the future of cosmology, I don't really think that we need to talk about number of modes. And it's not like we're collecting more modes. In a sense that, like, for example, you can do a lot with a single object. One example, bullet cluster. You take a snapshot of a single object, and you can prove that something like dark matter has to exist and can test or sort of rule out modified gravity models for explaining dark matter away, right? You can just do this with a single picture. I think that's a beautiful example of what you can do with a single object. I like that. Therefore, I like the idea of using one galaxy to actually do something similar. Take a picture and show me the image of dark energies. Show me the image of, some sort of modification of gravity effect. But think creatively about it. I think that's probably the way to go instead of counting more modes.
Ben, and then Roman.
Definitely an example of some kind of synchrony going on here, because I was just about to say that the cosmologists talk about modes a lot. And that's because cosmology basically in the perturbative regime is about modeling noise. It's modeling homogeneous isotropic noise. And then there's a unique way to describe that mathematically in terms of Fourier modes in the linear regime. And then when you go beyond linear regime, you can push things so far. But once you get into the truly nonlinear regime, I think Fourier modes are no longer really the correct mathematical tool to describe even cosmological phenomena. And because you're implicitly starting to average over so many different things that it's not really clear what it is that you're dealing with. And so the mathematical language, I think, needs to change. And when you're talking about the cosmic microwave background, it makes very little sense to give names to individual peaks, at least maybe for fun, but not for cosmology reasons. Peaks or valleys in the CMB, right?
Or initials.
But I mean, people have given names to galaxies, and with good reason, because they do all look pretty different from one another, right? Once you see them with enough resolution, and so when it's interesting because there are also connections to the concept of emergence, right? I mean, these objects. We're talking about objects. Our brains have evolved to talk about objects. Our brains are not originally really built to talk about Fourier modes. It's just through education that that we think that this is a normal thing to do when we talk about cosmological noise, like this large-scale structure, initial conditions, and So when you have these kinds of objects emerging through nonlinear processes, nowhere, if I show you the standard model Lagrangian, I challenge you to tell me that galaxies are going to emerge from that, right? I mean, this clearly is, and so the language needs to change, and I think that there's a really, a deep reason to go to higher resolution, to avoid the word small-scale modes, but to go to higher resolution and to learn about that connection of the small scales and, what are the features that we now are interested in? And maybe they're probably not the Fourier modes, but there could be other features. Nobody knows what robust features they may be on small scales that give us some important clues about cosmology. So I think that it's a fascinating frontier. And as a sociological side comment, I would say that the split in the community for decades between people doing cosmology and people doing galaxies, I think it's that has to be, that I think the end of that has to come, and it's coming. And I think we are living, this meeting, I think, is a manifestation of that, right? I'm very hopeful and excited about going to high resolution.
So, yeah, sorry, clearly my additional comment about modes has triggered some people. Roman.
Yeah, so briefly to come back to modes. There is this paper by Fabien Lacassa from Geneva, whose the title is The Small-Scale Miracle. And so he shows that the information content indeed goes up in the linear regime, then plateaus in the non-linear regime, and then scales up again if you go to very small scales. And so I understand, the argument that if you are in like the current survey, we are in a regime where the information is plateauing in the nonlinear scales. But if you go to smaller scales, then it shoots up again, according to this paper, right? So I don't know if people looked into that. So I think that the classical argument, even using modes, that there is no more information at small scales, I mean, this paper shows that it's true for a range of scales, but at very small scale, it goes up again, using very classical kind of Fourier analysis type of argument. So,
thanks, Roman. I think Ben wants to respond.
We got 2 minutes.
Because if this is about dark matter, then, in voids, there is infinite information, right? Voids have preserved all of the fine scale, information all the way down. Unfortunately, so if you find some way of accessing voids and the information that's stored in them about the primordial universe, there is, you can go very far. The question is just observationally, how do we access that information? Right? So I'm not sure it's relevant to talking about the bright objects that we can see in surveys.
I wanted to comment on one thing, Ben, you mentioned. I agree with everything you said, except the part where you said that sociologically there seems to be a convergence between the cosmology and the galaxy evolution. Yeah, and primarily I think theoretically in the theory space that might be happening, but in the observational space in like the next 10 years, all of the experiments are very, very cosmology focused, right? They're one single galaxy population, and you take the lowest signal-to-noise data possible to get a redshift, and then you call it a day. And yeah, I'm just curious what people think about that, aside from being bummed out.
Any takers? Oof.
Just picking up on Alex and Daisuke's comment that, an invitation to young people that I think the small scale information is not in all the higher order statistics I listed on my slide, but in coming up with maybe anomalous objects or new observational signatures and looking at the details of a particular dark matter candidate that may affect cluster splashback, another that may affect galaxy, cluster collisions, another that may show up in voids.
Okay, good. Shai's given us a couple more minutes, so we'll see. We don't have to finish. There's only 2 more, but
but if you need to step out, please don't feel obligated to stay.
So let's go to the sigma 8 tension, and I want to find the person who voted for boring, because I think it's just one. It's okay if you don't want to out yourself.
That's proof that this entire room doesn't subscribe to statistics. That only one person thinks that 2 sigma tension is boring.
2 sigmas happen too many times. Okay, anybody have any comments on the S8 tensions that we're seeing? We'll start. Okay, so we'll go to the next. Oh.
Why is S8 tension not H0 tension?
Because we didn't discuss H0 tension here. Nobody showed H0 tension. Yeah, I'm not going to start. I'm not. You almost got me to start. I'm not going to start.
Let's move on.
Let's move on to not. Who voted? There's several of you, so it's okay. Not concerning S8 tension. You could just maybe say why.
Was it you, Nick?
I mean, I didn't vote.
Oh, okay.
But I would have voted for not concerning.
Right.
Okay. No takers. No. Oh, good. Boriana.
I also voted for not concerning, to contradict my other arguments. No, but yeah, I think it's a 2 sigma tension at the end of the day. So I mean, it's interesting and it's getting us to think about a lot of things. But I think ultimately it's the science that we're after, not so much the tension. So I think as long as we get a better picture of things, I'm not concerned because we're going in the right direction, which is making progress.
Well
Optimism. I like it. I like it. Okay. No opinion. Okay. Well, you're not going to offer much to the discussion. Anybody want to concerned? I can see why it's exciting. Potentially new physics. Anybody want to say why they're concerned? No, everybody wants to go get a drink. Okay. We'll leave it with this last one. We thought we'd have some fun. Yeah, any thoughts on this? We'll just leave it with that.
I mean, you already get a Nobel Prize, right? So who cares now?
I didn't get a Nobel Prize. Did you get a Nobel Prize? Is it in the mail?
Maybe I can say like the grumpy physicist kind of. So the question is whether you accept like blind, black boxy kind of ML results, or do you need to interpret those results? And as physicist, I think it's unacceptable to have no interpretation. That's the whole point of a physicist. So that's why I think they will accept the results if there is interpretation.
Thanks for watching. So Anna wanted to talk a little bit about interpretability. Did that stimulate anybody to talk about interpretability?
Besides me.
I'm sorry I'm having to say this to Roman. Physics is simulations. And interpretability, this is a point of view. Interpretability is a mirage. We're talking about a stochastic field. And if you have a machine learning algorithm that's diagnosing cancer, you can ask, where's the tumor? When it's distinguishing between cosmological models based on a stochastic field, all you can ask is the physics in my forward model reliable? Both in terms of theory physics and modeling observations. What I really think is interpretability is really hard. And I don't know how to interpret a bispectrum anymore, So forget a deep learning black box.
I think this feels weird, but like in certain limits, people have shown that like neural networks converge to Gaussian processes. Also, like infinity, so like very unobtainable. But when they get sufficiently large, this Gaussian process limit appears, and then also this linear model limit appears. And I think, if you can take a Gaussian process and say you're okay with that in a certain limit, I think you should be open to the idea of accepting results from neural networks. And I also think, especially like cosmologists, but other people now care about sort of integrating neural networks with Bayesian methods, and I think that can only be of help. So from that point of view, I think eventually it could get there. But also, like, I stand by, if you can accept a Gaussian process, then maybe you can also accept a neural network.
No.
Any other?
Oh, okay. We'll let Tom get the last word in.
I mean, if for this discussion, if it's just about interpretability in the statistics used to describe fields, I think there's many statistics one can do that are very interpretable, that are very fast to compute, and they can characterize very nonlinear fields. At the end of the day, though, I think that's not the challenge we have. The challenge is that our forward models have to really be able to model the full observations. And that has much more complicated steps. But once we have a really good forward model that fits exactly, that models, looks identical to the observations, then at that time we won't care whether it was machine learning or some other summary statistics. All the statistics will have to agree that our forward model matches the data. And so I think we're sort of in a particular period of time where we still keep focusing about the tool of how we're going to be comparing this future beautiful forward model. But this is going to be the least important step once we have those good forward models. Yeah, completely. I mean, in reality, what you want is you actually model the photometric selection, the cuts, the instrumental effects, the point spread function, when was the bright time. Your model actually you're completely modeling. I mean, that's what I mean by complete forward model. So that you can really understand any bit in your data. So when your 2-point function doesn't go to 0 at large scales, or you have some other fluctuations on the sky, you have some hypothesis, and in your model you can convince your audience that you understand why your data looks like this. And I think as long as we'll have big data sets where the practitioners cannot explain to us the features in their data, nobody's gonna fully believe the inference. I mean, right? And so only having that full forward model that does take into account all the key bits that obviously manifest in your data, only once you have that full forward model, then you can convince people that, oh yeah, these people, they know what they're doing, they understand their data, that integration makes sense.
You stimulated more conversation. We'll go Danielle, then Daisuke.
So maybe, yeah, I guess another question then is how about machine learning insert as part of the forward modeling, like machine learning helping in like different steps of the forward model, as opposed to sort of waiting to have the perfect forward model and then we would trust any sum statistics or ML inference technique.
Sure, right? Imagining some of the stuff that Ben was doing, or you make some machine learning trick, or also what Wu showed of, that helps you speed up a bit. Of course, I think people will accept very quickly that. But again, the hard part is those are not the hard things. The hard things, I think, is fully modeling the data.
Also have the point of view of like forward modeling everything. I think that's what we need to do. We want to forward model in a way that is physically reasonable and that we can understand what's going on. So that's, I think, is the explainability and interpretability part, is that we have some idea of what's going on in the solution of partial differential equation that goes nonlinear. So it's not just mapping out what's in the Gaussian initial condition, but then how those are propagated forward in time through PDAs and solution to PDEs. It's easy to find the emulator and write it down that violates conservation law, mass conservation, energy conservation. There's no guarantee unless you put that in by hand. Current for machine learning, a lot of them don't necessarily respect all of those, even the conservation laws that we all know that has to be respected. And we can create a forward model universe that doesn't conserve energy. It's easy to write that kind of things down. We have to put some of, but as a physicist, I think we know some physical principle that our current machine learning does not quite respect. So I think those are the challenges that we might want to start really seriously think about physics-informed way of doing machine learning. There are something, maybe these are biases, but hopefully machine learning will teach us some more physics. But until then, I think we will have to kind of give some intuition to the physics instead of just using a big neural network as a large parameter fitting function. I think those days will come, but I think we have some work to do.
Okay, any last comments? All right, that was a fantastic conversation. Again, thank you, everyone. Thanks, Nick, for co-leading.